Welcome! Today we are solving LeetCode problem 347, top k frequent elements. This problem gives us an integer array called nums and an integer k. Our goal is to return the k most frequent elements from the array. The answer can be returned in any order, so we have flexibility there. Let's look at the constraints. The array can have up to 100,000 elements. The values can range from -10,000 to +10,000. And k is always valid. It falls within the number of unique elements in the array. One important note, the problem guarantees a unique answer, which simplifies things for us. There is also a follow-up challenge. Can we solve this in better than O of n log n time? We absolutely can, and we will cover that with our optimal approach. Let's dive in. Let's walk through example 1 to understand the problem clearly. We are given the array 1, 1, 1, 2, 2, 3, and k equals 2. Step 1. Count how many times each number appears. The number 1 appears 3 times. The number 2 appears 2 times. The number 3 appears 1 time. Step 2. Pick the top k elements. Since k is 2, we want the two most frequent numbers. The most frequent is 1, with 3 appearances. The second most frequent is 2, with 2 appearances. 3 only appears once, so it does not make the cut. Our answer is 1 and 2, the two most frequent elements in the array. Notice that the order does not matter. Returning 2 and 1 would also be correct. Now, let's look at an edge case, example 2. We have the array with just one element, the number 1, and k equals 1. Why is this an edge case? Because there is only a single element in the entire array. There is nothing to compare frequencies against. The number 1 appears exactly once. But since it is the only element, it is automatically the most frequent. And since k is 1, we only need one result. So our answer is simply 1. The key insight here is this. When k equals the total number of unique elements in the array, we simply return all unique elements. Every element qualifies. Your solution must handle this gracefully without crashing or returning an empty list. Let's start with the brute force approach, the most straightforward way to solve this problem. The core idea has 3 simple steps. Step 1. Loop through the array and count how many times each number appears. We store this in a dictionary where the key is the number and the value is its frequency. Step 2. Sort the dictionary keys by their frequency in descending order. So, the most frequent element comes first. Step 3. Take only the first k elements from that sorted list. Those are our answer. Let's trace through the example. Our array is 1, 1, 1, 2, 2, 3, and k is 2. After counting frequencies, our dictionary looks like this. 1 maps to 3, 2 maps to 2, and 3 maps to 1. After sorting by frequency in descending order, we get the list. 1, 2, 3. We return the first 2 elements, 1 and 2. That is our answer. This approach is simple and easy to understand, but let's look at how efficient it is next. Here is the brute force solution in Python. Our function is called topkFrequent, and it takes nums and k as inputs. Step 1. We create an empty dictionary called count. We loop through every number in nums. For each number, we use count.get with a default of 0, then add 1. This safely increments the count whether or not the number has been seen before. Step 2. We sort the dictionary keys by their frequency. We pass a lambda function as the key, which tells Python to sort by the count value. We set reverse to true, so the highest frequency comes first. Step 3. We return the first k elements using Python's slice notation. The :k means take everything from the start up to index k. 3 key things to remember here. First, count.get with a default of 0 prevents key errors. Second, reverse equals true gives us descending order. And third, the slice :k cleanly picks exactly the elements we need. Simple and readable, but let's check how fast this actually is. Let's analyze the time and space complexity of the brute force approach. Starting with time complexity. Counting frequencies takes big O of n. We visit each element once. Sorting the unique elements takes big O of n log n. This is the standard cost of comparison-based sorting. Slicing the first k elements takes big O of k, which is at most big O of n. The sorting step dominates everything else. So the overall time complexity is big O of n log n. Now for space complexity. Our count dictionary stores up to n unique elements, so that is big O of n. The sorted keys list is also a copy of all unique elements, giving us another big O of n. Overall space complexity is big O of n. Here is the key bottleneck. That sort step costs us n log n time. But this problem can actually be solved in big O of n time.
How?
Using a technique called bucket sort. That is exactly what our optimal approach does. Let's see how next. Now, let's look at the optimal approach, bucket sort. Here is the key insight. The frequency of any element can never be more than n, where n is the length of the array. If the array has 6 elements, no element can appear more than 6 times. This means we can create n plus 1 buckets, 1 bucket for each possible frequency from 0 to n. This avoids sorting entirely. Here are the 3 steps. Step 1. Count the frequency of each element. Same as before. Step 2. Place each element into its frequency bucket. If element 1 appears 3 times, it goes into bucket 3. Element 2 appears twice, so it goes into bucket 2. Element 3 appears once, so it goes into bucket 1. Step 3. Read the buckets from right to left, meaning highest frequency first. Collect elements until we have k of them. Look at the bucket diagram. We have 7 buckets for frequencies 0 through 6. Bucket 3 holds 1. Bucket 2 holds 2. Bucket 1 holds 3. The rest are empty. Reading from right to left, we first see element 1 from bucket 3, then element 2 from bucket 2. We have collected k equals 2 elements. We stop. Our answer is 1 and 2. No sorting needed. This runs in linear time. Here is the optimal bucket sort solution in Python. Step 1 is identical to brute force. We count frequencies using a dictionary. Step 2, we build our frequency buckets. We create a list called frequency with n plus 1 empty lists inside it. Each index represents a frequency. So frequency at index 3 means elements that appear 3 times. Then we loop through our count dictionary. For each number and its count, we append that number into frequency at the index equal to its count. Step 3. We collect the top k elements. We loop through the frequency list from the end to the beginning using range with a step of -1. This goes from highest frequency down to lowest. For each bucket, we loop through the numbers inside it and append them to our result list. As soon as the result list reaches length k, we immediately return it. 3 key lines to remember. First, the list comprehension creates n plus 1 empty buckets in one line. Second, frequency at CNT, append places each number directly into its correct bucket, no comparison needed. Third, the reversed range ensures we always collect the most frequent elements first. This entire solution runs in linear time, no sorting required. Let's analyze the complexity of our optimal bucket sort solution. Starting with time complexity. Counting frequencies is big O of n, one pass through the array. Building the frequency buckets is also big O of n. We create n plus 1 buckets and place each unique element into exactly one bucket. Collecting the k results is big O of n in the worst case. We scan through the buckets from right to left, touching at most n elements total. Every single step is linear. There is no sorting anywhere. So the overall time complexity is big O of n. Now for space complexity. The count dictionary stores up to n unique elements, big O of n. The frequency bucket list has n+1 entries, big O of n. The result list holds at most k elements, which is at most n, big O of n. Overall space is big O of n, same as brute force. The big win here is time. We went from big O of n log n down to big O of n. This directly solves the follow-up challenge the problem asked about. Can you do better than n log n? Yes, we can. Optimal summary. Time is big O of n. Space is big O of n. Let's connect the two approaches and understand the leap from brute force to optimal. Both approaches share the exact same first step. Count the frequency of every element using a dictionary. This always costs big O of n. No difference there. The key difference is what happens after counting. In the brute force approach, we take all the elements and sort them by frequency. Sorting requires comparing elements against each other. This comparison-based sort costs big O of n log n. That sorting step is the bottleneck holding us back. In the optimal approach, we skip sorting entirely. Instead, we use a clever observation. Frequency can never exceed n. So we create n+1 buckets and place each element directly into the bucket at its frequency index. No comparisons needed. Just a direct placement. That is big O of n. Then we simply read the buckets from right to left to collect our k most frequent elements. This is the leap. Instead of asking which element is more frequent, through comparisons we ask, what frequency does this element have? And place it directly. The frequency itself becomes the index. That single insight is what transforms an O of n log n solution into an O of n solution. Let's wrap up with a full comparison of both approaches. Looking at the approach, brute force sorts elements by frequency. Optimal uses frequency buckets. Time complexity. Brute force costs big O of n log n due to sorting. Optimal runs in big O of n. That is a significant improvement, especially for large inputs. Space complexity. Both approaches use big O of n. No difference here. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.